Chapter 24, Theory Video 1, Chemistry, Transition Elements. We are going to discuss about what transition elements are and how they take part in chemical reactions. We know that transition elements are found between groups 2 and 13, and they are found in the D block of the periodic table. But not all D block elements are classified as transition elements. The most important thing about D block transition element is that it can produce many, or it would have different oxidation states. That is one important thing. Another important thing is a transition element can be classified as a D block element that forms one or more stable ions with an incomplete D subshell. So it produces incomplete D subshell and it can produce one or more stable ions. Scandium, Se and zinc are not classified as transition elements because now scandium only form one ion Se3 plus, and it doesn't have any electrons in the 3D subshell. It is the configuration of Se3 plus is the argon atom. There are no, so it has to have, from this definition, it has to have incomplete D subshell. So that means there should be electrons in the D subshell, but because electronic configuration of Se3 plus, so the ion is going to have argon configuration, that is 3D1 4s2 configuration. It is not going to be scandium is not going to be a transition element. Then zinc would have has zinc ion zinc ion is Zn2 plus, and it has a complete 3D subshell. So we should have incomplete D subshell of the ion. So therefore it would have the argon configuration once again 3D10 4s2. So as a result, we have we say that it is not again classified as transition element because it does not have an incomplete D subshell. So one prerequisite that is needed for an element to be a transition element is it should have an incomplete D subshell. So we are going to look at the transition elements in the first row of the D block. Titanium to copper, and based on the definition given, we will be looking at, that is, the definition is the ions would have an incomplete D subshell. So now let's first write down a note on this. A transition element is a D block element that forms one or more stable ions with an incomplete D subshell. Please remember that we are talking about the ions, not the element itself. Scandium, Se and zinc are not transition elements because their ions Se3 plus and zinc 2 plus have the argon configuration, that is 3D1 4s2 and 3D10 4s2 respectively. Because scandium and zinc both do not have incomplete D subshell, they are not classified as a transition element. So as you can see here, now argon is 3D, scandium is rather the electronic, it would have electronic configuration up to argon and 3d1 4s2, because when it makes Sc3 plus, what happens is 3d1 and rs2 will go away. So the 3d1 it would not have any electron in it. So 4s2 and 3d1 go away. So argon is the configuration that you have. Then when it comes to zinc, zinc has the configuration of argon and 3d10 4s2 up to argon and then 3d10 4s2. Because it produces two plus ions, 4s2 would go away and 4s2 would go away and 3d10 is going to remain. 3d10 is filled. So as a result, because we do not have an incomplete subshell, D subshell, it is not a transition element. Then now we are going to figure out the electronic configurations. From the first row of the transition elements, we have to we are going to consider titanium, vanadium, chromium, manganese, iron, cobalt, nickel and copper. So they have the electronic configuration in this manner. So as you can see, titanium and vanadium, they have 3d2 4s2 and 3d3 4s2. So their 4s2s are filled and 3d3 comes along. Then when it goes to chromium, it is 4s1 and 3d5. Then manganese 4s2 3d5, then S block is getting filled. Then iron up until copper, iron up until nickel, you can see that it is 4s2 is getting filled, and then after that 3d 5 6 7 8 like that it goes. Then copper, it would have 3d10 and 4s1. So you should know these patterns. There is no one specific pattern here. 2 3 then 5 5 6 7 8 10. So like that only the 3D pattern goes. I hope you would be able to remember this. Please write down electronic configuration of the first row of D block, and please draw this table 24.1. Then after you pause the video and draw that, now we come to ions of transition elements. All transition elements are metals. So that means they have loose electrons, and as a result they can produce positively charged ions. But the speciality is, like I said earlier, each transition metal can form more than one positive ion. Now common ions for copper is going to be Cu plus and Cu2 plus. So transition means it changes. There are variable oxidation states, and these the interesting part about these changing or variable oxidation states is that they have different colors. These ions have different colors. Now if you take the ions of vanadium in their different oxidation states, the first one is VO2 plus, second VO2, that is oxygen 2 VO2 plus. So that means you can figure out the oxidation state of vanadium. Oxygen is 2, that is negative 4 is there. So negative 4 gets cancelled out, but a plus is remaining. Therefore it is vanadium 5 oxide is VO2 plus. So V has 5 plus. Then a solution containing VO2 plus is B. That is 2 plus is remaining. 1 oxygen is there. So 2 minus is there. That is going to be plus 4. Then number 3 is it has given its charge, it is 3 plus ion. Then 4 is D is 2 plus ion. So 2 plus, 3 plus, 4 plus and 5 plus, they have these distinct and variable colors. So then they have given the most common oxidation states of the first row of the transition elements: titanium plus 3 plus 4, vanadium 2, 3, 4, 5, and then we have chromium 3, 6, manganese 2, 4, 6, 7, iron 2, 3, cobalt 2, 3, nickel 2, and copper 1, 2. So this is also something that you need to remember. Write down a note. Transition elements are all metals. Therefore, they form positive ions. However, transition elements can form more than one positive ion, and they usually have different colors. Now, please draw this table 24.2. So the reason or the how this is possible for them to have this these variable oxidation states is that the similarity in the energy of 3d and 4s atomic orbitals. So because of their energy similarity, this is going to be possible. To identify them, because they have variable oxidation states, we usually include the oxidation number. So manganese 4 oxide, MnO2, and cobalt 2 chloride, CoCl2, like that we name it, right? So another very important thing that you need to understand is when transition elements form ions, first they lose electrons from the 4s subshell, and then only it goes to the 3d electrons. Now always remember the transition elements, their ions would have partially filled d subshells, right? So the vanadium atom is going to be 1s2, 2s2, 2p6, 3s2, 3d6, 3d3 and 4s2. When you go to V3 plus ion, what happens is 4s, now V3 plus, 3 electrons need to go. Now you know that 4s2, the first s orbital should go. And then because one further electron needs to go, that goes from the 3d orbital. So finally you have V3 plus, 1s2, 2s2, 2p6, 3s2, 3p6 and 3d2, and 4s0 is there. Then iron, it is for 3d6, 4s2. Then Fe3 plus ion means 4s2 is going to go away and another one from 3d is going to go. Copper, it is 3d10, 4s1. As you can see, 3d is filled, but we are talking about the ion. Therefore, when Cu2 plus ion is formed, 3d9 is going to be there, because 3d9 is D is incomplete. We can call that a transition element. In all of them, the most common oxidation state is going to be +2. When the atom is going to lose the 2 4s electrons. Usually the maximum oxidation number of the transition elements will usually involve all the 4s and 3d electrons in the atom. Now, when you take vanadium's maximum oxidation state is +5, it involves 2 4s and 3 3d electrons. After iron, the +2 becomes most common because 3d is going to be more difficult to be removed, because the nuclear charge increases across the period. Nuclear charge increases across the period. As a result, it is mostly the 2 plus 2 charge is the most common one. Then in complex ions or compounds formed with oxygen or fluorine, we can see higher oxidation states in the transition elements. Now, when you take chromate 6 ion CrO2 minus and the manganate 7 ion MnO4 minus, you can see that the manganese would have 7 charge, 7 plus, and chromate 6, it would have a 6 charge. They are complex or compounds that are being formed. I hope you understood. You should go to question number 1, but before that, write down this note. Variable oxidation states are possible because of the similarity of energy in 3d and 4s atomic orbitals. Put a star and write down. When ions are formed, first 4s subshell electrons are lost, then 3d electrons are lost. If you want, you can write down this vanadium, iron and copper formulas by pausing the video. Initially, at the beginning of the row, 4s and 3d electrons are both involved in the formation of ions. However, after iron, plus 2 becomes the most common oxidation state because it is more difficult to remove 3d electrons because the nuclear charge increases across the period. Leave a line, put a star and write down. Higher oxidation states of transition elements are found in complex ions or compounds formed with oxygen or fluorine. Example, chromate 6 ion CrO4 2 minus and manganate 7 ion MnO4 minus. I hope you understood. If you understand, please do question number 1. If you did not understand, please let me know.